Okay, let's get into this. Imagine this for a second. A time when the northern lights weren't just up near the poles.
Hmm.
Picture them, like blazing across Europe, maybe even shimmering over parts of North Africa.
Wow.
And here's the kicker. The ground itself, our planet, offered way less protection from the sun.
Sounds pretty wild, almost like science fiction.
Totally. But it's not. This actually happened around 41,000 years ago.
And that brings us to the main event, right? The La Champs excursion.
Exactly.
We're talking about a time when Earth's magnetic field, that invisible shield we rely on, almost completely collapsed.
It really almost did. And for this deep dive, we're looking at some fascinating insights from the brighter side of news. The article's called Earth's Magnetic Field Failed 41,000 Years Ago for Ever-Changing Human Evolution.
A pretty bold title.
It is. So think of this as, our guide to understanding what happened, how this near meltdown went down, the effects it had on, well, everything on the planet, early humans.
And what it might mean for us, maybe even for looking for life elsewhere.
Yeah, exactly. We're aiming for those aha moments, but don't worry, we'll keep it flowing.
Right. So the goal today is basically to unpack the La Champs excursion, its impact, using this article as our foundation.
Okay, so this whole thing, it really hangs on the Earth's magnetic field. We sort of know it's important, but maybe break it down. What's it actually doing up there?
Well, in simple terms, it's a shield, a vital one. It blocks most of the charged particles flying off the sun, what we call solar radiation or the solar wind.
Like a force field.
Pretty much, yeah. An invisible planetary force field. Without it, we'd be much more exposed.
Okay, but how does Earth make it? It's not some giant magnet in the ground, is it?
Huh. No, not quite. It's generated deep inside, in the outer core. You've got this molten iron sloshing around.
Right.
That movement creates electrical currents. And those currents generate the magnetic field, which stretches way out into space. That whole region is the magnetosphere.
The magnetosphere.
Yeah.
And that's crucial for, well, life as we know it.
Absolutely crucial. It holds onto our atmosphere, stops the solar wind from just stripping it away over millions of years, like what might have happened to Mars.
Ah, okay.
And it helps protect the ozone layer, too, which, blocks harmful UV radiation.
Sure.
So, yeah, fundamental for life.
And not just life, right? Our tech depends on it, too. Satellites, power grids.
Definitely. Big solar flares, these things called coronal mass ejections, they can throw huge amounts of energy at us. The magnetic field deflects a lot of that, protecting our satellites, preventing power grid surges, that kind of thing.
Huh. So it's doing a lot of quiet work up there.
Yeah.
Now, the article mentioned reversals, but also these things called excursions, like La Champs. What's the difference?
Good question. So a full reversal is a massive, slow process. Takes hundreds of thousands, maybe millions of years. The north and south magnetic poles actually flip. An excursion like La Champs is much faster and kind of incomplete. The field weakens dramatically, the poles wander all over the place, but they don't necessarily settle into a full reverse position. It's more like a temporary wobble or dip.
Got it. A shorter, sharper event. So this La Champs excursion, when was it again exactly, and how bad did it get?
The main period was around 41,000 years ago, lasted maybe 2,000 years, give or take, between about 42,200 and 41,500 years ago.
And the strength.
That's the really startling part. The article says it dropped to maybe just 10% of what it is today.
Wow, only 10%? That feels incredibly weak.
It is very weak, and the poles didn't just weaken, they went wandering, right?
Yeah, the article mentioned that, like they weren't pointing north or south anymore.
Exactly. They moved around significantly, and for about 300 years during that excursion, things got really weird. The field apparently tilted rapidly and became multipolar.
Multipolar, what does that mean? Like lots of little north and south poles scattered around.
Sort of, yeah. Instead of one main north and south, like a bar magnet, it was more complex, jumbled, more like the magnetic fields of, say, Uranus or Neptune. Much less organized and much weaker overall.
Huh. Okay. And that chaotic, weak field, that means more stuff from the sun gets through.
Precisely. Those high-energy particles that our normal field deflects, they could penetrate much deeper into the atmosphere.
Okay, so you've got this weak, weird magnetic field, more radiation pouring in. What did that actually do to the planet, to life?
Well, the article suggests some pretty major consequences. That extra radiation hitting the atmosphere likely changed its chemistry, maybe even altered weather patterns, atmospheric circulation.
So the climate could have shifted.
It's certainly possible, yeah. And down on the surface, you'd have much higher levels of cosmic rays, more UV light. That's tough on living things.
How so? Like increased risk of cancer,
Yeah.
DNA damage.
Exactly that sort of thing. It would have created significant biological stress.
So a really challenging time to be alive. How did early humans cope? Did it cause extinctions or push evolution?
The article doesn't point to a single mass extinction event just from Lachamps, but it definitely stresses that this pressure would have driven adaptation, adapt or potentially disappear.
Which brings us to the humans around at the time.
Right. Homo sapiens, us, and also Neanderthals still in Europe.
And the timing is interesting, isn't it? Because Neanderthals disappeared not too long after this period. Could the weakened field be involved?
That's the really compelling idea explored in the research mentioned by Agnet Mukherjee and Raven Garvey. They see a potential link between this magnetic field low point and a spike in certain human behaviors, specifically Homo sapiens behaviors.
Okay, like what? What were our ancestors doing differently?
One big thing seems to be clothing. The archaeological evidence from Homo sapiens sites around this time shows more tools like needles, awls, scrapers, stuff you'd likely use to make tailored clothing.
Tailored, so not just draping hides, but actually sewing fitted garments.
Exactly. Which offers better protection against cold, obviously. But Garvey points out another potential benefit.
UV protection.
You got it. Better fitting clothes cover more skin, offering an unintended shield against that increased solar radiation. Allowed people to maybe travel further from shelters, too.
Huh. So better warmth than accidental sunscreen? Clever. What else?
Ochre, that red mineral pigment. Humans used it before, sure, but its use seems to become more widespread, more intensive right around this time.
And ochre.
Wait, don't tell me.
Yep. Experiments show it actually blocks UV light quite effectively. So the researchers suggest it might have been used as a kind of prehistoric sunscreen.
Wow, seriously. Slathering themselves in red mud to block the sun. That's incredible.
The evidence points that way. And Mukherjee notes this interesting overlap. Areas with more human activity back then match up with where auroras would have been more visible and where we see increased use of caves.
Caves make sense. Natural radiation shelters.
Exactly. So you have this picture, seeking shelter in caves, maybe wearing tailored clothes, possibly using ochre as sunscreen, all while these amazing auroras are lighting up the sky. What about the Neanderthals, though? Did they show the same kind of inventiveness?
That's the crucial difference the article highlights. Based on what we found so far, the Neanderthal toolkit doesn't show that same increase in tools for tailored clothing, and the ochre use doesn't seem geared towards sun protection in the same way.
They might have been more exposed.
It suggests a potential vulnerability, yeah. They lacked those specific adaptations that Homo sapiens seem to have developed or intensified right around that stressful time.
And it wasn't just sunburn, was it? The article mentioned more serious health risks from the radiation.
Right. Garvey makes that point. Beyond sunburn, high UV can cause serious eye damage, and critically, it can deplete folate levels.
Folate, the B vitamin.
Yeah, essential for healthy pregnancies, fetal development. So if Neanderthals were more exposed, it could have impacted their reproductive success over time. Having that extra protection from clothing or ochre would have been a real survival advantage for Homo sapiens.
Man, it just paints such a different picture of that time. And the skies. These auroras everywhere. How did they figure that out?
That involved some pretty sophisticated modeling. Mukherjee and Sanja Panovska used something called the Space Weather Modeling Framework. It was developed at the University of Michigan.
Okay.
They basically simulated what Earth's space environment would look like with that super weak, tilted magnetic field.
And the result was auroras gone wild.
Pretty much. Instead of being stuck near the poles, the simulation showed auroras could have been visible across huge areas, much of Europe, maybe even northern Africa. Imagine looking up at night and seeing those lights, somewhere they never appear today.
Incredible. Beautiful, but also kind of ominous.
Exactly. As the article notes, that stunning display was a direct sign of the danger the shield was down, and harmful radiation levels were way up. A beautiful warning sign.
So, thinking about this event 41,000 years ago, feels like a bit of a warning from the past, doesn't it? What if something similar happened today with our technology?
That's a major takeaway from Mukherjee's research, definitely. A magnetic field collapse now. Well, it would hit our modern society incredibly hard. We're so much more reliant on technology vulnerable to space weather.
Okay, run through it. What goes wrong?
Well, communication satellites. Big trouble. Lots of failures. Ground-based communications like radio could be disrupted. Power grids are a huge concern, risk of massive blackouts from geomagnetic currents.
Like the Carrington event, but maybe worse or longer?
Potentially, yeah. Navigation systems, GPS, anything satellite-based would become unreliable, maybe totally useless.
That affects everything. Shipping, aviation, even just driving.
Everything. And air travel itself would be riskier due to increased radiation at flight altitudes. Basically, the interconnected digital world we rely on. It's surprisingly fragile without that magnetic shield fully functioning.
No GPS, maybe no internet, power outages.
Yeah.
It's, yeah, a stark picture. Really makes you appreciate that invisible field.
It absolutely does. This research is a powerful reminder, really, that we need to understand these dynamics, these fluctuations, because they can happen and the consequences could be immense.
But there's another angle too, right? The planetary science bit. The fact that life did survive, even thrive
Yes.
through this.
Yes. That's maybe one of the most fascinating implications. For a long time, the thinking has often been strong global magnetic field way necessary for life. You need it to shield against radiation.
Seems logical.
But Lachamps shows us, well, maybe not always, life here, including complex life like our ancestors, weathered the storm with a field at only 10% strength.
So it makes us rethink what's truly essential for life on other planets.
Exactly. It forces a reevaluation. Maybe
Yeah.
some planets we've written off because they have weak or no magnetic fields. Maybe they could still harbor life or have in the past. It gives us a totally different perspective for studying exoplanets.
Huh. So the search for alien life just got potentially wider.
It could have, yeah. As Mukhopadhyay puts it in the article, looking at Earth's past, these extreme events, helps us study exoplanetary physics differently. He says, life did exist back then, but it was a little bit different than it is today. It suggests maybe our definition of habitable has been a bit too Earth-centric.
Okay, wow. So let's try and wrap up this incredible journey back in time. Key takeaways seem to be this dramatic magnetic field weakening, the Lachamps excursion, around 41,000 years ago.
Right. Big environmental challenges from all that extra radiation.
But then these amazing adaptations by Homo sapiens, tailored clothes, maybe even ochre sunscreen.
Which might have given them an edge over neanderthals, potentially.
And then the bigger picture stuff, how vulnerable our modern tech is, but also how this event forces us to rethink what life might need to survive elsewhere in the universe.
It really highlights how dynamic Earth is and how surprisingly resilient life can be, and how small changes, small adaptations can make a huge difference over time.
Absolutely. Which leaves us with a pretty big question to ponder, doesn't it?
Yeah.
If life survived this, what other things we think are essential for habitable planets might not be?
Or, flipping it around, how might those seemingly small adaptations, like sewing clothes or using pigment differently, be the key to survival, not just way back then, but maybe even facing future environmental changes?
Definitely something to think about. A lot to chew on there.